format, like finalisms.
If we have 4 quizzes, as you can check in the manual.
It's just like schedule for finalisms was published in registrar, and I checked it, and there is written that we have a finalism for physics in.
Okay, so we will double check this with instructors, but
We will
best
not
to,
have.
yeah, best to my knowledge, as it was planned, we have 4 quizzes. Based on these 4 quizzes, there will be final grade. There will be one more exam, but only for those people who, because of some valid reasons, didn't make one of the quizzes. So then you will have a chance to retake it. So that will be after end of semester, kind of additional option. But that is not final exam. That should be based on 4 quizzes. But I will also double check this. Hey, hello guys, nice to see you. So let us recall um, shortly our previous discussion. So we introduced thermodynamics and we consider such key thermodynamic parameter as temperature. So who will tell me what temperature is and what it quantifies? Temperature. So it provides us some quantitative information about average kinetic energy of particles which form this matter. It's either atoms of gas or some molecules of solid, whatever. Um, we cannot measure temperature by definition if there is no matter. If it's free space, then temperature doesn't make any physical sense. So we know that temperature can be measured with thermometers. We consider liquid thermometers. Who will tell me what is the main reason? Actually, there are 2 main reasons why mercury is the best working liquid for measuring temperature.
Which that is the metal.
It's a metal, and what does it mean?
Thermal conductivity.
Thermal conductivity is much higher than, for instance, another commonly used working liquid, which is alcohol. Yes?
Also think it does not evaporate for in the room temperature demands because.
Well, it unfortunately does. That's why when you break the thermometer, you need to not to waste time and actually collect all this mercury, which went out. Yes. Okay. So another point which should be highlighted, another feature, is that mercury does not wet the glass, surface of glass, and that helps keep this interface between like the edge of the mercury clearly visible, so we can clearly read the temperature on thermometer. Okay, so we continue further today, and so far we considered thermal expansion, like reaction of different objects on change of temperature, but so far they were either solid or liquid. However, we also have gases as medium. We need to consider gases today and proceed further with definition of heat and mechanical work in our scope of thermodynamics. So let's talk about gases. So if we have liquid, for instance, or solid state, then we can introduce such parameter as initial volume. So at given temperature, liquid and solid material will occupy some initial volume. Then, of course, if temperature increases, this volume will increase because of volumetric thermal expansion. Is it possible to apply this concept of initial volume to gases? No, because gases, no matter how much of gas we put in some closed container, they will occupy all volume by definition. So initial volume doesn't apply. So we need to consider some other parameters to describe the state of gas. So by the way, a reason why gases, as opposite to liquids and solids, possess such option to fill the whole volume instead of occupying some given volume similar to how liquid does. So there is a fundamental reason for this behavior. The interatomic interaction between atoms which form the gas, they are very weak. And that's why they don't stay together and gas can occupy whole volume. So now we will focus specifically on so-called ideal gas. And many gases at low temperature, they exhibit behavior of ideal gas. So what is specific about ideal gas? So we consider that there is no interatomic interactions, means that they are so weak that we can neglect with them completely, and atoms interact only with each other in the moment of collision, so-called kinetic model of ideal gas. From another parameter which should be taken into account, that total volume of all molecules, or atoms of ideal gas, should be much smaller than the volume this gas occupies. So we consider them as some mathematical points which just interact with each other in the moment of collision. So these are general definitions of ideal gas. And when we deal with gases in some volume, it's convenient to quantify the amount of this gas via moles, which is quantity of matter. And definition of moles is the ratio between mass and molar mass. So you can find this molar mass in the periodic table, and we also need to know how many atoms are in 1 mole of any matter. So who will tell me how do we call this number? Avogadro's number. That is Na, and that is equal to 6 something, where is 6022 10 to 23. Quite a big number. So that's number of atoms in 1 mole. So now let us consider step by step 3 most common processes which can happen with gas, or since we consider ideal gas, with ideal gas. So first process is when temperature is constant. So that is so-called isothermal process. And for that, since other two state parameters, there are three state parameters which define the state of gas. There is pressure, volume, and temperature. So one of these state parameters is constant, means that two others are changing. So in that case, pressure is changing reversely proportional to volume. Or in other words, we can write, for instance, like this. So P1, or we can maybe even P times V is equal to constant. So that is the first process, isothermal. Keep in mind that all of these processes which we consider and relationship between varying state parameters, they were not derived from any model, theories, or whatever. These are purely empirical results. They were experimentally measured, observed for ideal, for gases which are satisfying conditions of ideal gas, and experimentally obtain this information. So obviously, there could be other processes when, for instance, we consider pressure constant. So in that case, change of or like volume of the ideal gas will be directly proportional to temperature, and we can write that V divided by T is equal to constant. One more option when volume is constant. So similarly, we can write for pressure over T remains constant. So these are experimentally observed dependencies, and summarizing them will lead us to so-called ideal gas state equation, which we can write as P times V, pressure times volume, equals to M divided by capital M, which is mass divided by molar mass, times R times T. And this R is universal gas constant, and it is equal to 8.314 joule per mole Kelvin. So looking at this definition of ideal gas constant, please tell me what do you think is the physical meaning of this constant? How much energy is required to increase the temperature of 1 mole or 1 Kelvin? Or in, well, kind of very similar to this, generally accepted definition of physical nature of this physical meaning of the ideal gas constant is work which is done by 1 mole of ideal gas when you increase its temperature by 1. So that please remember, it's kind of important definition of this constant. Obviously, we can express this equation for the state of ideal gas in different terms, not in terms of number of moles, but in terms of total number of molecules. So we can write that M over capital M is equal to or maybe not like this. Let's write that total number of molecules will be equal to M over capital M times NA. So number of moles times Avogadro's number. So from here, we can express that M over capital M is equal to total number of atoms divided by Avogadro's number. And now we can substitute it in this equation. So we get the same equation in a bit different form. P times V is equal to M. Okay, sorry. Instead of M over capital M, we get N over Na times RT. And we see here two constants, one in numerator, another in denominator. So we have universal gas constant and Avogadro's number. So the ratio of these two constants gives us one more constant, which is commonly used, and that is Boltzmann constant, equal to 1.38 10 to minus 23 joule per Kelvin. So now we can express also one more time in a bit different form the equation for the state of ideal gas, which is P times V equal to KB times, actually we can write here total number of atoms times KB times T. So that's the third form of the equation of the state of ideal gas, which is also quite widely used. So that is about like introduction of main features of ideal gas. And next question we need to discuss is internal energy. We introduce internal energy, heat and work. So let us guess what will be the definition of internal energy of a system. Let's say some body. We have a solid body, and we want to define what will be the internal energy of this body. How would you define? Um, well, that's a bit further we will consider. Let us first clearly define what is internal energy. But which energies? Kinetic and potential energies. Do you believe that is sufficient, or we need to add some explanation? That's all correct. Some of kinetic and potential energies, but which specifically? Let's say this object possesses some potential energy with respect to the flow and kinetic energy when it falls down. Would these two potential and kinetic energy contribute to internal energy of this object? That's what you said initially. We have sum of potential and kinetic energy. Oh, that is important. So we do not consider velocity of translational or also kinetic energy of rotational motion or potential energy of the center of mass with respect of some level. We consider kinetic and potential energy of the particles inside the system. Means kinetic energy is they vibrate there if it's a solid state or liquid state, and also we have interaction, interatomic interaction, so that provides also internal energy. So that is important to know what is exactly internal energy. So how can we change internal energy? You already mentioned that we have some heat transfer. And what is heat transfer? It's transfer of energy from or to the system through the interface between the system and environment. So there's always some interface between the system and environment, and energy transfer is considered as heat. So initially, it was considered that heat is transferred by some special fluid, which is caloric, called caloric fluid. And that's why historically heat is measured in calories. So uh, that was the reason why it possessed some special unit for measuring heat, because uh, nobody knew at that time that there is a direct relationship between mechanical work and heat, so-called work-heat relationship. G has shown that indeed mechanical work against friction forces results, this dissipation of kinetic energy transforms into internal energy, and there is direct correlation between them. So technically, there is no reason to invent any new unit to measure heat, and we can use conventional units which we use for mechanical work, which is joule. However, historically, we still have some fields where calories are quite commonly established. And for example, which example you will give me? What field is where calories are widely used? Yes, the energy of our food. That would be quite surprising if someone specifies how much joules this uh, chocolate provides. So usually it all measured in calories. However, again, there is no really need in such a unit. There is a relationship, of course, between calorie and joules. So 1 calorie is equal to 4.186 joule. So we already clarified that internal energy, we defined it. It's energy, kinetic and potential energy of the particles which forms the um, material. Um, Heat is an option to change internal energy. Let us discuss in more details how we quantify this heat. So for that purpose, a heat we will denote with capital Q. We can represent it as capital C times delta T. Capital C stands for heat capacitance of an object as a system, and delta T is change of its temperature. So what is heat capacitance? Is actually it shows us the thermal inertness of the system, means how much the system resists to change its temperature. Analogy, you could maybe recall definition of mass. We claim that it's measure of inertness of the body or system to change and resistance of the system to change its velocity. So something similar we can recall here. It's inertness and resistance of the system to change its temperature. So this is a valid equation. However, this heat capacitance is for whole system. Usually we want to know some properties of the material of which this system consists of. So in that case, in order to provide some specific parameter, we introduce specific heat capacitance, which is small c, and that is heat capacitance divided by mass of the system. So then we get heat capacitance per unit mass. And that is called specific heat capacitance. That's why Q will be equal to mass times um, specific heat capacitance times delta T. um, if this delta T is big, if we change temperature of the system in a wide range, then there is a good chance that heat capacitance, let's consider just heat capacitance is capital C, will be a function of temperature. And in this case, for general um, definition of heat, we can write that it will be equal to integral from temperature 1 to temperature 2, heat capacitance as a function of temperature dt. So this is general definition of heat when we already take into account an option of uh, heat capacitance as a function of temperature. Usually, if we have narrow change like of temperature, range of temperature change, then this could be neglected and consider heat capacitance as a constant parameter. However, that's not true for big changes of temperature. Now let us consider some specific example in order to see how temperature of a system changes as a function of applied energy to the system. So let's plot temperature in degrees Celsius versus energy in joule. So our system will be some block of ice placed in a closed container, considering that mass of the container is much smaller than mass of the ice. Let us assume that initial temperature of this ice was minus 30 degrees Celsius. So in this case, we place it in this container, it's sealed container, we start to provide energy, like transfer heat into this system, and monitor how temperature of this ice, like what's going on with the temperature inside. So let us consider first process. Let's call it part A of the. So we provide some energy and temperature increases from minus 30 up to 0 degrees Celsius. So that is up to a moment when we start the phase transition between ice and water. So there is phase transition from ice to water. So in this region, this part of the process, we have only ice. We increase its temperature and amount of, sorry, what is this? Detached. So the amount of heat, Q, during process, part of the process A, will be equal to mass of ice times specific heat capacitance of ice times delta T. And in this case, delta T, that's this part, we go from minus 30 to 0, so that will be 30 degrees Celsius. Temperature increases. So once we reach this point, when phase transition happens, and further provide energy to the system, what happens with the temperature? Will it increase further? It will remain constant. And what is the reason for that?
Change the
Phase change. And then we need, when we provide energy to the system, when it's in the phase change, energy is consumed by this process of phase change, um, and we cannot change temperature of the system until full conversion of one phase to another will happen. So that's why further here we will have a plateau. Temperature will not change while energy is provided to the system. And here we have a mixture of ice plus water. So that will be process part B. And amount of heat transferred during this process will be latent heat of ice, which amount of energy per unit mass of ice in order to be to experience phase transition to water. And obviously we need to multiply it by mass of ice. Once we reach the point when we converted all ice to water, we already can increase temperature further if we provide more energy to the system. So here temperature will further increase, and it will be already only water. We don't have any ice in this container. And tell me what will be the temperature we can reach in this process, which we can mark as process C. That will be 100 degrees Celsius. That is boiling temperature at normal conditions. So in this case, this process QC, amount of heat transferred will be M water, mass of the water, times heat capacitance of water, times change of temperature. Here, change of temperature will be 100 degrees Celsius. And keep in mind that we have different heat capacitances of water and ice, just because this, like specific heat capacitance, because they possess different physical properties, these two phases. If further we increase the temperature, sorry, not temperature, but further provide energy to the system, the temperature will not increase, because we come to the next phase transition, and that will be water plus steam. So that will take some energy from us in order to realize this phase transition. So this will be part D of the process. QD is equal to mass of water times latent heat of water. So that's energy which is required by this system in order to have phase transition from water to steam. And what happens further? And we don't have any phase transition, we have only steam. Bless you, this is only steam, and this is some process, let's say E. We just heat up the steam. By the way, we can heat it up quite a lot. We don't have any limits because there are no further phase transitions there. So here will be QE equal to mass of steam, specific heat capacitance of steam, times delta T. This concept is realized quite often in so-called autoclave system, when we have some instant pot for fast cooking. You have sealed pot where steam cannot escape, and that's the case when you can heat the system higher than 100 degrees Celsius. Got a question?
Um, how high can the temperature of steam get?
Oh, that's good question. It can get as high as you can handle. So, for instance, this instant pot, they always have a security valve because
1,000.
that is bit extreme, technically possible. You just need to find some container which will resist insanely high pressure, which will result eventually because of such temperature of steam. And that is already quite challenging. So, hot steam is used in power stations. So, when you use like either coal, gas, or even nuclear energy, you heat up the steam to high temperatures where it's like hundreds of degrees. And this steam is released on the valves of turbine, so it starts to rotate turbine. Turbine connected with a shaft to uh, electrical generator. So that's how you can generate electricity. Uh, However, of course, you need to take into account very high pressure, and that's why the walls of the containers and pipes should be properly um, designed. So, in order to avoid some explosions in kitchens, there are security valves at certain threshold level of pressure. This valve is open and releases some steam from this system in order to prevent too high temperature and too high pressure. Because at some point, the sealed container can explode and cause a lot of damage. So you can reach quite high temperatures with steam. So that is something about quantifying heat. And there is another parameter which we need to introduce, and that is work done on the system. Um, so let us consider, because we said there's one option to heat transfer to change internal energy, another option is to perform some work on the system. So let us consider some container, like cylinder, with a valve, like, well, it's like some piston, not valve. So here we have some ideal gas, and there is certain, why it doesn't work, certain force F exerted to this piston. So there will be some, if this is in equilibrium, there will be some counter force F, which is equal to P times A, where A is cross-section area of the cylinder, like area of the piston, and P is pressure of this ideal gas. So if we consider here X is X, then work done by external force on the system can be represented W dW as minus F times dx. We can substitute instead of F its expression in terms of P times A, so it will be minus P times A times dx. So what is this? Area times displacement, so it's actually change of volume. So this is dV. So we can write that here it will be minus P times, times dV. And eventually for work on the system from this external force can be expressed as integral from initial volume to final volume here we have this minus P times dV. So that is the definition of work done on the system. And um, keep in mind that we put here pressure under integral because pressure changes also as volume changes. So only in case of isobaric process we don't have change of pressure. So let us consider some example of isothermal process when temperature is constant. So we have some two states, one state and second state, and there's some transition between these two states. Here we have pressure, here volume. So this is P1, P2. This is V1, V2. And obviously, according to this definition of mechanical work by the system will be defined as the area under this curve, which defines the transition between state 1 and 2. So now when we introduced definition of internal energy, heat, and work, we can formulate first law of thermodynamics, which tells that change of internal energy is equal to heat plus work. And this is nothing else as another formulation of law of conservation of energy. We consider some closed system, change of its internal energy can be realized only via heat transfer or some mechanical work. So let us consider some example when internal energy remains constant. So we have delta E internal is equal to 0. Tell me, please, which process is this? We discussed this process. I didn't explain it in terms of internal energy, but we mentioned this process during our today's discussion.
Isobaric. No, it's the process with constant volume.
That's isobaric process.
Yeah.
But why do you think so?
No, I meant with the constant pressure.
So yeah, so isochoric process for constant volume, but isobaric is constant pressure. So explain why do you think that this is the case when this process with constant internal energy is isobaric process.
Because in that case, the work would be 0.
Well, work would be 0 also for isochoric process, because change of volume would be equal to 0. So, but that's only about work. But we have, besides work, change of internal energy also defined by change by amount of heat transfer. So which process will result in constant internal energy? Isothermal process. Because if you recall at the beginning of this lecture, we gave again the definition of temperature. And that is measure of average energy, kinetic energy of the particles which form the system. So if temperature doesn't change, energy of these particles also doesn't change, and internal energy remains constant, or its change is equal to 0. So in this case, when we have isothermal process and internal energy doesn't change, we can write that Q is equal to minus W. So what does it mean? That there are different options. Either we transfer heat from outside through the system, through the interface between system and external environment. Then system will perform work because of this transfer, and that will be negative work because it will be work against external forces. Then temperature will remain constant, and all absorbed heat will be used to perform work. The other option, when the system is losing energy, we are transferring heat through the interface to the environment. And then, in order to keep temperature the same, not change, and as well as internal, then the external forces should perform work on the system. So that comes from the first law of thermodynamics. Next time we will discuss more in details different processes and introduce one more so-called adiabatic process in the scope of first law of thermodynamics. But now we can summarize our discussion, and the main message here at the beginning we introduce the ideal gas because that is the model system with which, on the example of which we will mostly discuss all thermodynamic processes. We introduce internal energy as the important parameter of the system, thermodynamic. So it's energy, total energy, kinetic and potential of this building blocks of the matter, like atoms of which form the solid state or ideal gas. In ideal gas, potential energy is equal to zero, no potential energy, no interatomic interactions, only kinetic energy. And there are two options to change internal energy, which is heat transfer and work, which is performed on the system. So based on that, we also introduced quantitative description of heat. We are introducing heat capacitance and specific heat capacitance as a measure of inertness and resistance for change in temperature of a system or unit mass of the material, and also define how we determine mechanical work, where this integral minus integral from initial to final volume P dV. Putting all these things together based on the concept of conservation of energy, we end up with the first law of thermodynamics, which tells us that change in internal energy is equal to heat plus work. If internal energy is not changing, remains constant, heat is equal to minus work. And also you need obviously take into account the sign. Either we provide heat to the system and system performs work, or we take energy away with heat transfer from the system, and then external forces should perform work on the system in order to keep temperature constant. Thank you very much for attention and have a good weekend. See you on Monday. We will continue.